have drip irrigated alfalfa. The purpose of this experiment, main purpose is to evaluate the effects of water stress on alfalfa grown here in Nevada. Like I said, it's the most important crop in the state in terms of the economic value that it produces, but also because it's irrigated in 40% of the land and of the irrigated land in the state. In addition to that, it consumes it consumes relatively much more water than other crops. Now, one of the reasons why it consumes more water is that, first of all, it's a perennial crop. So it grows, you planted, let's say, 1 year, and then it produces the next year, and the next year, and the next year. So it kind of like, you cut it, and then it regrows, and cut it, and it regrows.
It keeps growing.
So here in Nevada, we get about 4 cuts. So that's 4 incomes for people. And that's one of the big differences with other crops, where you have only, let's say, like an annual crop like corn. You plant it in the spring, and then you are harvesting by the end of the spring, and then you're harvesting by the fall. But then you have only 1 income out of it. But in this case, if you want to have that regrowth, then you have to get so. Just those basic, ideas, I think, explain why it requires more water than other crops. Another thing is that it has a deep root system. It can reach, let's say, the root can get water up to, let's say, 2 meters, which other crops can't reach the water that deep into the soil. So that's another, that's one of the particularities of alfalfa, and that's why it also consumes much water. Another thing, and that's one thing that I find very interesting, is that, let's say, it has been happening more and more here in the western United States, that because of the droughts that we are having and experiencing, people have to cut their irrigations. Like water is cut short, let's say, by mid-August, when it's usually cut, in September. So with many crops, if you don't have the water until you have a good development of your crop, you will have no income whatsoever, right? In this case, with alfalfa, if you cut the water short by August, then you can have at least 2 cuts, maybe even 3 cuts. So you are losing, but you are not losing everything.
Completely. Yes.
Now, if you were to stop, if I were to stop irrigating, so we're gonna cut actually this alfalfa tomorrow. If I stop irrigating, then we can do that, and it will just enter like a dormancy stage, where it just stops growing, and then if we start irrigating again during the spring, then it's gonna grow. So
it doesn't die completely.
It doesn't die.
Will it be stressed? That's why.
It will be stressed, but then eventually, because it has no water, it has this mechanism where it realizes, well, there's no water, so we're just kind of save that energy, and then stop the regrowth. So does that make sense? I mean, there are different reasons, and also, let me be kind of clear. I'm not advocating, for the use of alfalfa. It's just that this is the crop that is consuming the most water in the state right now. I'm also working with other colleagues, let's say with sorghum, with hemp, with other alternative crops that require less water. But because this is where most of the water is being consumed, that's why I personally have started. I started working here at UNR for about 2 years and a half. So that this is the crop that I kind of have been starting to work. Now, the purpose of this experiment, I kind of stopped there, but so we're evaluating, as I said, the effect of water stress on the alfalfa. So we have different irrigation treatments. We have one treatment which is over control, where we are providing to the alfalfa all the water that it needs for optimal development. That's kind of the objective, to avoid water stress, so to maximize yield by avoiding the water stress. Then the second treatment needs 80% of that. So if we are applying, let's say, 1 inch of water for the 100%, for the 80% we are applying 0.8 inches.
0.8 inches.
And then we have another, the third treatment needs 60%. So in that case we apply 0.6. And we have 3 replicates of those. So that will be a total of 9 irrigation blocks. One irrigation block will be 1 and 2 plots. Now we have 2 lots because in addition to those treatments, we have 2 alfalfa varieties.
Oh,
One
okay.
alfalfa variety is supposed to be more drought tolerant than the other.
Okay.
The other is supposed to be this one, and it's actually planted in this column.
This is one variety.
This is one variety. This is marketed as being highly productive.
Okay.
But in order to achieve that high production, it requires a lot of
A
water.
lot of water. Yeah.
And that one was breeded to be drought tolerant, the one on the next. And then with that one, what we have found is that it's indeed, it requires less water than this one. But it's marketed, like I said, as being drought tolerant, highly productive. Now you can see that there is some difference in the plant height, right?
The crops,
Just
right?
between this
Yes.
one and this one. But what we have been finding, and we only have 1 year of data, so we need more than 1 year. But so far what we are finding is that they achieve about the same yield. We haven't found a significant difference between in yield at each irrigation treatment. So that means that at 100%, both varieties
Same
achieve
yield.
about the same yield. And 80%
80%
about the same
same
yield,
yield.
and 60% about the same yield.
Okay.
So let's see.
There's a problem there.
I'm sorry?
Oh yeah, it's been cut by.
Yeah, actually, I should probably go and move that with you guys.
Yeah.
Okay. That's the season to show the next
Thank you. Yeah, so let's see. Let's go through. I can show you. Sorry. Oh, and these are drip irrigated.
Oh, everything here is drip irrigated.
Yes. Drip irrigation is not common in alfalfa, and actually, I mean, not surface drip irrigation. So this is surface drip. The reason why we're using drip irrigation is because when I started here, it was the only irrigation system that I could use that will allow me to control the amount of water that we need to apply, like effectively. Actually, this field was flood irrigated before, and flood irrigation
Are they flow rates?
is very inefficient. Those are timers.
A timer.
So there is a valve in there.
Yeah.
We come here like we have soil moisture sensors, and I'm gonna talk about that in a little bit. But from the soil moisture sensors, we know how much water we need to apply
Yeah, that's almost the same.
in order to refill the soil water content to full capacity.
Yeah.
Then, based on that, we calculate how
Time.
much time we
According to
need to
flow
leave the drip tape running.
According to the
So we
flow rates.
control it. Yeah, according with the flow rate of the drip tape and then the spacing between the drip tape. But like I said, it's not something common. It's something that we're using here for research purposes. But still, the findings, we expect that they're going to be still useful. Now, a system like that one, the sprinkler irrigation system, that's much more common. Because in that case, the problem with the drip tape is that when you harvest, you are cutting the alfalfa, but then the drip tape may get into the into the knives that are cutting. But in that case, that's not an issue. You just move the sprinkler system out of the place, and then you can cut right away. So, but anyways, this is the first year that we are using that irrigation system. So that was not available when we started this experiment. We started this experiment in 2020. So that's why I couldn't use that one.
Okay.
But now for that new experiment which I will describe in a little bit more, we are using that.
You have some crops here.
Yeah, it's alfalfa. Yeah, we're
Okay,
gonna
okay.
stop by there in a little bit.
So
Okay.
I have a question about these sensors. Are they just for claimant analyzers or this sensor?
So, well, let me, before we move on there, before I answer your question, so these are 100%. So this is the control. It's kind of like the highest yield that we can achieve, on the conditions that we have. But the reality, like that's what we have been intending to achieve the maximum yield and avoid any water stress. The reality is that this variety demands much more water than that one, that the drought tolerant. So there is no water stress in the drought tolerant variety, but this one does experience water stress. That was not the purpose, but the reality is that because we are limited by the irrigation system that we have to apply them the same irrigation amount.
Yeah,
So it's basically like you provide water to this variety and then it just starts consuming that water much faster than this one. So we couldn't, unfortunately, base irrigation on this one because we will substantially over-irrigate the drought tolerant. We couldn't base irrigation on this one because we will increase the water stress to this one. So we can average, and that's our control of irrigation.
So what method do you use to determine the water stress on the plant?
Well, we are using two methods. The main method it's called the average soil water depletion. What you estimate is, so if you imagine the soil as a container, like as a volume, then the average soil water depletion tells you how much water has been depleted from that control volume in a certain amount of time. So, according with some guidelines that have been used over many years, for many crops, as long as you keep that soil water depletion below 50%, in other words, you have about 50% of the water that can be stored by the soil available to the plant. As long as you keep that 50% of the water available, the plant will experience no water stress. So that's kind of like, we know that we can achieve that with the drought tolerant. We haven't been able to achieve that one with the other one. So that's one way to quantify or know whether you have a water stress. The other way is through these sensors, and that's what goes back to one of the questions. So this is a canopy temperature sensor. So this allows us, we point it directly to the crops, and it's measuring the canopy temperature every minute.
This is the method I know about, the canopy temperature measurement.
Yeah, there has been some work in that regards actually.
This is
before
temperature sensor.
Canopy temperature sensor. Yes, before I arrived to UNR, I was working with that for using these canopy temperature sensors mounted on a center pivot on an overhead irrigation system like those one, like that one, and then we calculated irrigation amounts based on the canopy temperature. Why does that work? Because the canopy temperature is an indicator of the water stress. So basically, the higher the temperature, the higher the water stress that the crop is experiencing. So, and we have to have them in pairs. So these two, as you can see, they are pointing at the same area. So we're using the average of both because that allows us to get rid of some effects, of some angle effects and some noise that we're gonna have. So this is one type of sensor that we are using to assess the effect of water stress, and we have them in different. So we have them for the two varieties and for the three irrigation treatments. And we also have, let's walk a little bit. So this is a data logger for a soil water sensing station. So it has connected three soil moisture or soil water sensors. Now these sensors, like you can see here the cable, and then underground we have the cables going to the center of the plot.
Okay.
And they are buried at three depths, 20, 60, and 90 centimeters. Because we don't want to know just how much water is available at one depth. Like if surface, then you have the effect of evaporation. So
Yeah.
then water will be depleted faster, and there is also higher root density. So we are estimating the soil moisture content, like I said, 20, 60, 90, and from there we can make that calculate that average soil water depletion.
Yeah. Okay.
Yeah. And the nice thing about these sensors is that they don't need any calibration. They are they have been shown to be quite reliable. I mean, we sold them in 2020, and then the sensors they just continue working. We have had some issues with the data loggers, but not with the sensors. The sensors they just keep running and running and running.
So,
Yeah. Now with the data loggers, the nice thing about this is that it's an all-in-one data logger. So it's a solar power data logger. It's manufactured by the same company that makes the saltwater sensors. So it's kind of like an integrated system. And yeah, you can purchase them like that. But also they have a technology. It's called a time domain. The sensor, the saltwater sensor, it's called time domain reflectometry. That technology, just like computers, when it was initially available, it was extremely expensive, like completely out of reach for, let's say, for a farmer. But now, one of these sensing stations with 3 sensors, I will say you can get it for maybe $1,500, which is still not cheap, but it's nothing like tens of thousands of dollars, which that technology used to cost. So you have that, this type of technology that eventually, like, I mean, as the company maybe starts to sell more and more, it may become more affordable. But I'm very excited about that technology. I think that it can really make a big difference, because right now a lot of that's one of the big challenges in irrigation, like helping people to know how much they need to irrigate and when they need to irrigate, and make that more accessible.
so this data loggers they send the data directly to the cloud.
This one does. Yeah, it's an Internet of Things enabled. It's an SDI 12 sensor, but then this sends to, it's called Hologram. It's a web service, cloud service, and we get the data directly from there.
Okay.
Now I'm gonna have to pause a little bit to stop that.
Okay. Sure.
But that's about this experiment. Okay. Let me just stop that one.
Okay.
That's about it, about this experiment.
So-
and I was saying, so that's 100%,
Yes.
and this is a 60%.
This is 60%. So
And-
we have 80 over there.
No. So we had a randomized.
Oh,
design.
it's randomized.
Yeah, so it's 100, like that one, 100, 100. This is 60.
Okay.
And then, let me see if I can remember 8%. So this is 100 as well. That one in the corner is 80.
Okay.
So, for example, there you can compare the 100 and the 80.
Yes.
And you can see, I mean, there is really not that much of a difference. In the end, there is an effect in the yield. I mean, there is a decrease in the yield. So far, we haven't seen a significant effect, or statistically significant between the 100 and the 80. We have seen it between the 100 and the 60, not between the 100 and the 80.
So the focal point of the study is to determine what percentage is optimal to have plants still producing in the most effective way.
Well, you know, one thing is that usually when or the way that most of the technology, at least in irrigation, has been developed, or the way that the objective of agriculture in general, irrigation in particular, has been always to maximize yield, right? But I personally think that we need to think in a different way, like maximizing yield, maximizing water use efficiency. I mean, and this goes, if you are in a region where you don't have any water issues, then I guess it's okay to maximize yield. I mean, there is no restriction. But if you had the significant restriction that we have in the Western United States and many parts of the world of having a limited water supply, then in that case you want to maximize water use efficiency. Well, water use efficiency, it's the ratio between your yield and the water that you
The
use
water
to
you're
produce
using.
that yield. So in other words, you are maximizing, let's say, the tons of, in this case, alfalfa that you are obtaining per meter of water that you are applying. So that's what we need to be looking at, I think. And in that case, that's part of also what we are assessing, like the crop water productivity between the different irrigation treatments. And in that case, probably a moderate, mild or moderate deficit will achieve a higher crop water productivity or water use efficiency than, say, the 100% control treatment.
Okay. So, could it be possible at the end of this research to tell alfalfa farmers in Nevada to say, hey, the 100% water you're using is inefficient. The crops will do well or will have the same yield at 80%. That way, they completely drastically reduce at least 20% of water that they're using. Strictly.
Well, certainly one of the things that we expect to get from this research are recommendations for farmers. But the way that I will put the recommendation is, they are facing, many of our farmers and ranchers are facing water curtailments, like cuts in the water they have. So one recommendation that I can give for them is, let's say, if they have only 80% of the water that they have available, or 70% of the water, I can let them know whether one variety, whether the drought-tolerant variety will perform better than a different variety. So that's the type of recommendation that we can get from this study. But also how much yield they can expect to produce, by practicing deficit irrigation. That's the name of what we are doing here, deficit irrigation. So we are not meeting the full.
Based on what they were getting from the field here.
Software you're using, real time.
So right now we don't have the process fully automated. So it's semi-automated in the sense that we have we use a spreadsheet where we enter the information. Now I have a I actually have been working on computer programs for agriculture. I am teaching a class here at UNR. It's called Applied Python Programming for the Agricultural Sciences. So it's certainly one of the things that I expect to eventually have a computer program that kind of automates everything that we are doing so far. And I have been kind of submitting grant proposals with that idea, like hoping to get funds for that. But that's the idea, to have a computer program to provide those recommendations automatically. Another thing that we are doing here is that we are collecting data quite frequently, plant height, canopy cover, leaf area index, and we are tracking the development of the crop so that we can feed that into a computer crop model. So a crop model is a computer program that allows you to get an estimation based on the environmental conditions, based on the soil that you have, based on some characteristics of your crop. Then it gives you an estimation of how the biomass, the yield, or in the case of alfalfa, the biomass is the yield. But how much you can expect the yield to kind of increase over time based on the management decisions that you follow. So we are feeding this information that we are collecting from this experiment into a model that we expect eventually we can integrate into a computer program that pulls up program will pull the crop model in order to make run different scenarios. Like what happens if I only irrigate 1 inch tomorrow, or if I irrigate 0.8 inches or 0.6, like how is that going to have an effect at the end of the season? But that's going to take some time because first of all we need the crop model ready. So we're working on that direction, but it takes time. I mean, it's you need years of data collection, and that's one of the problems in agriculture is that you only have, let's say, 1 year, like per year, you usually have one set of data that you can feed. It's not like in other, you know, branches or other areas where you have a lot of data. Maybe within a single day you have thousands of different measurements. In agriculture, that's a big limitation. That it takes a lot of time to collect the data, and even if you do it properly, you only have a few sets of data, which is not. It will be very challenging to use machine learning. Still, you can use it, but it will be very
It'll be
challenging.
challenging, yeah. Data gaps. Here on the field, there are some of these beds that are not censored. Like here, I cannot see any sensor here or here.
Oh well, you know, it will be ideal to have sensors in all of them, but that will be just
Costly.
too expensive. So we are putting one in each for each treatment and then for each variety. So we have a total of 6. So we are assuming that what we are getting from one is representative
In
of
the other.
So I mean,
Okay.
it's a big assumption, but yeah, otherwise it would be just too
Okay.
expensive.
I've seen in other situations where, since excessive use of sensors is expensive, using a computer program, we can sort of extrapolate based on 1 or 2 parameters in a field that is in an area that is not censored. We can extrapolate in large fields, trying to measure the soil porosity. They've done that with satellite imagery, where they have a bunch of sensors in part of the field, and then they can extrapolate how the field behaves as it progresses, coupling that data with thermal imagery from
Right.
from the satellite.
Well, you know, it's certainly a possibility, I will say, in a commercial field where you have, you know, you don't have these big alleys and everything is kind of like you have the same condition in a large area. In that case, it makes sense. You have one sensor, then you have some satellite imagery, or you can use a UAV.
A drone.
And based on that, you can extrapolate data. In our case, because of the very particular needs that we have, which is, you know, we need to take the measurement like right in the middle of the plot. Like that's not, at least right now, as far as I know, with the technology that's available, we can do that. But I mean, that will be great. There are other type of sensors, and I'm actually planning on using a different type of sensor that will allow us to take more measurements. But hopefully we will have that running by next year. At least right now, that's what we are using. But it has been providing us really amazing people. Like I said, they are very reliable.
What is your take on the commercial application of this, having smart irrigation systems in large plantations where the farmers can afford them? Is that something that farmers with large plantations necessarily need? Having their own smart irrigation system with a bunch of humidity sensors that can help them make decisions on their own, but not relying on data that has been collected in a study and just advising them. Do you think that some farmers need to have their own, but not intricate versions like this? Some more tailored down version for an everyday farmer to be able to use and have his field being watered automatically.
Well, you know, in terms of how to, I guess, apply some of the things that we are using here, you know, in a for commercial purposes, I will think that those soil moisture sensors it's certainly one technology that I think it doesn't need too much in order to be really available. The canopy temperature sensors, I wouldn't advise, you know, a producer right now to use it, like, because there is not, we are still missing, you know, like the technological support to use properly all the information that the sensor can provide. Now, with that being said, actually during my postdoc, I was working on a computer program that was actually doing that, providing the irrigation recommendations automatically based on the measurements from the canopy temperature sensors. As far as I know, that's the only type of framework that it's available in that regards. And And well, I left that and I joined UNR, so I'm no longer, let's say, actively collaborating in that regards. But that's still, we still have this need, like this big gap in terms of once the technologies are available. First of all, we as researchers, we need to make sure, that before we provide recommendations, we need to test them ourselves before we can recommend them to use them. Now, like I said about those saltwater sensors, I do not have any problem in recommending those to a producer. Yeah, but still, with that being said, there is still the need for having some simple app, that where you use your cell phone and then from there you know how much
Yes.
you need to irrigate based on the last measurement. But that's another thing that I am planning on working on. Actually, I just last week I submitted a proposal, a proposal for that. So that's one of the things, the funding. There are many possibilities, many ideas, but at the end you need funds in order to support the students that can work on that, because it's limited what we can do, without the support of students.
Okay. So can we know more about what is happening on this
Sure.
site?
We can work. So, are you guys familiar with this type of overhead sprinkler irrigation system?
I have read about them. I've never seen one in my
Okay,
country.
well, are you gonna be visiting other places here in the US? Other than Rio?
No, we are almost at we're touching the end of our visit already.
Okay.
Yes.
No, the reason I'm asking is because there are some states where this type of sprinkler systems are the most widely used irrigation systems.
You have
Ne-
some in the country.
Have you seen that? Okay. Well, if you fly over Nebraska, Texas, Kansas, you will see these large circles.
Yes, the circles.
As you fly, and then you see in the plane window, you will see these large circles. Now, this is a very similar type of system like the ones that create those circles. Those are called center pivots. So what they have is that one of the first tower, it's basically grounded, like it's static all the time, while all the other towers move.
Okay,
And that's why it starts making this movement like the hands of a watch.
Okay. It moves across the radius of the circle.
Right, and that's what causes what creates these large circles.
I see.
So those are called center pivot irrigation systems. This is very similar, but the main difference is that in this case all the towers move. And so it moves basically perpendicular to this fence. So then it's gonna move and you get an entire rectangle. Now you won't see a system with this size like usually. The thing is that in order for a system like this one to be, let's say, you need a large surface because the system it's costly. It can get expensive. So you need to get a large area in order to eventually, recover the cost of the system. In this case, because it's research, we're not too concerned about that. The interest more than anything is being able to control our irrigations in an effective way. And this system allows us to do that. First of all, as you can see, the sprinklers are located very close to the ground.
Yes.
The reason for that is because with typical sprinkler irrigation systems, so you have this sprinkler going, in such a way that as soon as there is wind, you have a lot of water lost because of the wind drift. Now, putting the sprinkler so low to the ground, that's one way in which this technology has evolved in order to reduce those water losses by the wind drift. And actually, I have been irrigating some days it's really, really windy, and I have seen some other sprinkler systems, and a lot of the water is just lost by the wind drift. And here, it's pretty, still the applications, the water applications are still quite active. field. So that's one big advantage that it has. But another thing that this irrigation system has, it's called a variable rate irrigation system. It has a GPS. There is, you can see here, that it's kind of like a bulb.
Yes.
That's a GPS there. That lets know the control panel. This is the control panel, so that's the electrical component that. Let me open it. Sorry. That's the control panel. So this is basically this electrical computer machine that controls the operation of the tire. Unfortunately, I can't leave it open for too long because of the
Because
water.
of the water, yeah.
But with that GPS unit and that control panel, basically the machine knows the position where it is in the field, and then we can program it so that it applies one irrigation amount, let's say for this first plot, another irrigation amount for the following plot,
Oh.
and another for the next plot.
Oh,
Actually, based on the position, like I said, and based on we have to use a computer program where we enter how much water we want to apply to each plot. But based on that, the control panel is gonna regulate the operation, control the operation of some valves. And those valves will control like the first 9 sprinklers. If you don't mind doing your shoes wet. So let's say you have 1, 2, 3, 4, 5, 6, 7, 8, 9. These first 9 sprinklers are operated by, are controlled by the same valve. So we can basically, we can apply here even
nice.
the same amount in these
Yeah,
first
okay.
9 sprinklers. Then the same amount for the following 9 sprinklers. And another amount for the other 9 sprinklers. So that way, we're actually going to control one zone, one sprinkler zone there, another sprinkler zone here. So that's going to be the first 18 sprinklers. And that's how we're going to be able to apply here. If we determine with those saltwater sensors that we need here 2 inches, we can apply 2 inches here. If we determine that based on the treatment that we have, that we need in that following plot, let's say 1.8 inches, we can do that.
So-
But that's something that we can do. Well, there is actually no other irrigation system that has that option available, commercially available. So you can do that with any other type of irrigation system. And that's precision irrigation, or kind of like what we think about when we hear about precision agriculture. You know, it's basically get rid of this concept of the idea that all the plants are experiencing the same conditions over an entire field. With precision agriculture, you are trying to quantify how much of different
exact need.
inputs that the plant needs, the amount of those inputs. In our case, for precision irrigation, we want to quantify how much water is needed here. But then, in addition to knowing how much water is needed, you also need a way to provide that water.
Yeah.
And that's one thing that wasn't available. Well, it has been available, I think, since 1995, something like that. But there hasn't been too much adoption. And part of the reason is that, well, first of all, it has a cost and it's expensive. But also, you need to have a lot of variability in your field in order for let's say, for that big expense to kind of like make sense. It's one of the things that there is more and more research going on in that regard. But like I said, you need a system like this because there is no other way you can. Right now, you can quantify the water needs. That's all. And you can do it just like you guys were talking about. different ways to do it, right? So that's not so much the problem. The problem is this one. So how to control the water that you apply.
How are the plots here determined? How does the machine know that the plot spacing? Because we have a couple of different plots. Where was this program based on how it was planted here? Manually, like okay, with this is the spacing for the first plot, and that was inputted to calibrate 1, 2, 3, 4, 5, 9 of the sprinklers to align with the first plot, or how exactly is that done?
So the way in which the program is going to know that it's based on the length.
Okay.
So, ideally, if the system works well, this sprinkler it's always going to be irrigating a straight line because it's supposed to be a line that is going to be perfect, that it's going to be parallel to the fence. So that line, it's going to go along parallel to the fence. The same with this one. So all the machine needs to know it's at which length with respect to, let's say the zero will be close to where the drop is. That will be the zero, the initial length. And here maybe, I don't know, like 200 feet. So it knows at 200 feet that you want to apply, let's say, 1 inch. But then at 220 feet, you want to reduce to 0.8. Okay. But that's going to be based on the GPS.
So was the entirety of the plot mapped out based on that GPS?
No,
or is it progressive?
We let's say the way we came up with this layout, it's we needed, here we're going to have 5 irrigation treatments, then five irrigation treatments, 2 varieties, and then 3 repetitions. So that gives a total of 30 plots. So we needed a way to arrange those 30 plots efficiently. And just kind of based on my calculations, I came up with the arrangement of being able to put 3 plots, like 3 rows of plots. Row 1, row 2, row 3. And then I know that row 1 can be irrigated by the first 2 sprinkler zones.
Okay.
Then the second row is going to be irrigated by sprinkler zones 3 and 4. And then the last one by 5 and 6. We have a total of 6, I think, sprinkler zones. So it's basically just kind of like arranging them in a way where we have 2 sprinkler zones, which consist of 19 sprinklers, irrigating
the gap between the rows, are the sprinklers that walk around those gaps turned off, or do you still have water?
Yes, they are going to work because we can't, we can potentially just close these ones, just close them.
Yes.
But no, we want them operating. The reason being that we can potentially close this one. But the reality is that some of the water that is coming from this sprinkler is also going to reach that. And this one as well. So that's why we want to, it's more like this one. So that's why we are keeping all of them open, and we're just closing the ones on the borders, which we really don't need.
Okay.
But we will see. I mean, we are just starting to use it. What is the first season that we're using this one? So we may eventually find out that we don't need to close them. But right now, not like we're not supposed to have anything solids. So what we're concerned is this, the plots. And we are going to have here, like I said, 5 irrigation treatments. And it's a similar experiment to what we have here. But we have one, so we have also a 100% control, and we also have 2 varieties. One of the varieties, the drop tolerant, is the same one. But the highly productive, we have a different variety. Because we also want to test different varieties, not just the same one. But we wanted to keep the drop tolerant because we have been seeing that it's indeed consuming less water. So we have that 100% of control. We also have the 80% and the 60%, just like here. So that's 3 treatments. But with the 80 and the 60% that we have here, and that we're going to have here, what we are doing, it's a constant deficit irrigation. So that means that all the time we are applying 0.8 and 0.6 of the full irrigation. Now, crops, different crops have different stages when they are more sensitive to water stress and more tolerant to water stress. In the case of alfalfa, right after you cut, it's very important that you avoid water stress. That can help the crop. So what we're going to test the other two treatments, we're going to test something similar to that 80 and that 60%. But what we are going to do is that we are going to base the irrigations on the growth stages. So we're going to have a variable deficit. So let's say after a cut, rather than applying 0.8, we may apply 0.9 in order to have more water available, and then reduce the irrigation amount after that when the crop is more tolerant to water stress. So that's what we want to test there. A more, let's say, smarter way of practicing deficit irrigation. And eventually we want that to be to receive feedback from this crop model that I told you about.
Yes.
Eventually we want to see if we can have two irrigation treatments that are similar to that 0.8 and 0.6, but that have received some feedback from the crop model in order to have that smart variable deficit irrigation. But that's what we are testing.
Interesting.
Yeah. And we also have, so we have 5 treatments and 2 varieties, and now we have 10 sensing stations. So took a while to put these sensing stations, but another thing is that here we have 4 sensors. We have them also at 20, 60, and 90 centimeters, but we also put one all the way to 2 meters.
Oh, all the way to the tip of the root.
In order to, what we wanted to know is whether the crop is actually getting water all the way to 2 meters. Then that way we can know whether we have deep percolation or not. Because it's something that here we are assuming that we don't have it, but we don't have the data, to show that. But if we can show it here, that's going to help us.
Okay.
But these are the 2 experiments we are applying. In this case, in here we don't have the variable rate irrigation system. In here we are going to use a precision irrigation system. But I will say that precision irrigation is not just being able to change your irrigation amounts. It's also being able to provide the precise amount of water that is needed by the crop. Even if you treat the entire field, the same, it's still just knowing how much water is needed by the crop. That's a big improvement over a lot of ways being done. It's the way things are run nowadays. That's one big improvement. But also being able to control effectively. So if you know how much water you need to rely, and you have a system like this one that allows you, or drip irrigation that allows you to control how much water you're applying, I will say you are making a very precise and effective use of irrigation.
Yeah, definitely.
So, how can we follow up on the research you're doing here? How can we keep ourselves up to date with what is happening here?
Well, my students are going to present some conference actually in a few days. There is one conference paper coming out from there.
Okay.
We also have a poster with some preliminary data. I can share that information with you guys, but later I do expect that we will have journal papers coming out.
Okay.
Yeah. And also, feel free to reach out to me. I will give you my business card. I have it on the truck. But feel free to reach, if I can help with anything.
Yeah.
I will be glad to.
Because I'm planning on doing a similar research in my country. So I would love to collaborate with you on something like this.
Yeah, sure. We can. I can certainly, provide some advice in terms of the equipment that we're using, how to use it as well. And yeah, just questions in general that you may have. I'm always glad to have collaborations, and I grew up in a developing country where we have also significant water problems. So I'm always interested in being able to apply the kind of things that we are finding here, in other places. Now, one of the things it will be difficult. Like for example, this irrigation system, like I said, it's expensive.
It's
I mean, not
expensive.
many places you can find it. But drip irrigation system, it's not too expensive. I mean, I wouldn't say it's affordable, but still, it's more affordable than something like this. Particularly, I mean, if you don't have a large field.
Okay. That's great.
That's great.
I think I've exhausted my questions for now.
I'm sorry.
I think I've exhausted my questions for now.
Okay.
Yeah. I'd just like to know more about how this can be automated almost completely with a computer program.
This machine.
No, I mean all of the type of irrigations that we're doing here, how the decisions can be made with, how the data can be analyzed, and then we can have decisions made automatically by a computer. That would be really cool.
Well, you know,
I do a lot of Python programming, so
mhm.
I'd really love to dig more on that.
Well, I will say that project that I was working on before I joined UNR, it was a big step into that direction. Now that was with a center pivot. A center pivot it's much easier to automate. This one is not, because you have to, just like we did right now. Like I had to come here and stop it. A center pivot, because it's always running as a circle. Then you can just leave it running. There is actually people that leave it running like from the start of the growing season till the end of the growing season. Like it just keeps running all the time.
How are they powered? Because this one is this is a diesel generator.
Yeah, this is a diesel engine.
Do some of them are solar powered?
There is also the option to have electric power on
Okay.
this one, but it was just more expensive. It was kind of like 50% more in terms of cost.
Oh.
But with a center pivot, you can also have this one, but I wouldn't recommend it. I think it will be just better to have electric power.
Okay.
Yeah, but yeah, like I said, that's probably much easier to do. Not easy. I probably shouldn't
Cheaper?
say easier. It will be much less difficult to
Okay.
automate something with a center pivot. Because yeah, I mean, we had the system to the point like we had the canopy temperature sensors mounted here.
Mounted, yeah.
And then as the pivot started to run, it was collecting the canopy temperature, and we had everything automated to the point where like the data was processed every night, and then eventually after running the pivot, it will come up automatically with a prescription map.
Oh. Cool.
And then the user will see that in a GIS program, and then the user will decide, yes, I want to go ahead with the prescription map or not. But that was one way to effectively use the variable rate irrigation system, because in that case it's automatically detecting the variability of the field, which otherwise you can't. And that's one of the real limitations of the sensors. Yes, I mean right now you have only data from one point, but maybe in a larger field or in the future, yeah, it may be possible to use more machine learning to interpolate data. But so far, that's a big challenge.
Okay.